If you have ever been inside a car, you'll know that as the car moves, you will feel different pulling forces depending on the car's direction. This effect is most noticeable when the car accelerates or makes a turn. But why do we feel them? Today's video is on the fictitious forces and the physics behind them. Let's start by defining the problem. We will analyze different frames of reference in order to understand what these fictitious forces are. More specifically, I'll use the blue cap person to reference a system with no movement, and the red cap person for the system that is moving. Here, I listed 3 different situations to understand how different frames of reference explain a simple phenomenon. Let's take a look at a translational case first. As we can see, we have drawn a universal frame of reference in the middle to have a clear view of the event. Our objective is to define what each of them see and how to make them agree with each other. To get a better understanding of what is going on, we will start with a ball that does a basic movement like it is shown here. This ball moves up and down, then right and left. We can now switch to a multiple perspective system to better understand the situation. The border color of the squares indicates the point of view of different individuals. Notice here the position of the ball from the 2 different perspectives. How can both of the system agree on the movement of the ball if they see different behaviors from it? The answer is letting them know that their own system is rotated of about 180 degrees from the other. This rotation results in 2 different coordinate systems that can agree on the events given a change in sign in the y-axis. While this example is quite simple and intuitive, it will help us in understanding the next situation, the velocity case. Let's draw the same system as before, but this time our red cap person is inside a moving train. This train can come back and forth, but for our study, let's imagine it just moves in one direction. The same ball movement of earlier is now repeated. How will this movement affect what they see? For the blue cap, there is no difference in what he sees, but for the red cap, the situation is completely different. As you can see, there is a steady shift in the ball due to the movement of the train. Is there a way we can make this system agree on what they have just seen? It is in this context that we introduce inertial frames of reference. These encompass all systems that are stationary or move at a constant speed in relation to one another. It is very important to mention that while the laws of physics remain the same, in this system, certain physical observable, like trajectory, may completely change from one system to another. In order to make these 2 systems agree on what they just saw, we can use the Galilean transformation listed here. We will analyze each part in just a second. Physical variables like trajectories, unfortunately, are not conserved in an inertial system. Let's take a look at one, and let's draw it. Both of the systems agree on the height that the ball reaches. What they don't agree with is the length of the trajectory. Notice here the difference in scale in the second frame of reference. This means that the overall trajectory is stretched out due to the speed of the train. As we were saying, we can use Galilean transformations to connect what both of them see. This transformation can be done by both systems to understand the other's frames of reference coordinates. X is the position vector, and it has 3 components, x, y, and z. T is the time. To obtain the system coordinates, we can use this transformation. Let's look at all these terms. R is a 3x3 rotation matrix, which values depend on the rotation done between systems. V is the velocity vector that the second system has compared to the first. A is the translational vector for position, and ultimately S is a time translation. We are now well equipped to understand the case where one system accelerates compared to the other. A clear example of the effects that an accelerating system has is shown here. To fully answer the question that we posed to ourselves in the beginning, we need first to use an easier example. Let's take a look at what happens when one of our subjects is inside an elevator. This elevator is able to move up and down with a constant acceleration. To understand what happens, we will now analyze this problem with a more physical approach, by defining the forces inside the system. By splitting the system into two different parts, we can better understand how the system works and analyze each of the parts separately. The forces that are acting on the body are the gravitational force pulling it down and the normal force pushing it up. The elevator instead feels the force exerted by the cable pulling it up and the force of gravity united with the normal force pushing it down. By using Newton's second law, we can write in a system both of the equation for each part. As the elevator moves, both the body and the elevator itself move with each other, meaning that their acceleration will be the same. On the screen here, I listed all the transformations that I did, and I tried to be as clear as possible to show not only its dynamics, but also that in this specific case, the force that is pushing the body up directly is actually the normal force. Let's analyze now the same system, but with our observator inside the elevator. From their perspective, even though the elevator moves up and down, their acceleration, compared to the one of the elevator, is equal to 0. Hence, they don't know they're accelerating. But how is it possible that by breaking down the system, the forces that are acting upon the body are the same as before? Shouldn't there be a different force that's acting upon our body? While the forces that are acting upon our system are the same, the dynamic equations aren't. Let's first start by noticing that the acceleration that both the body and the elevator have are actually equal to 0. The other difference is in the gravitational acceleration. In fact, when we accelerate up or down, the gravitational acceleration value actually changes. This apparent change in the gravitational acceleration is felt by the person inside the elevator as an increase or decrease in its weight. As we rewrite the equations with this newfound knowledge, it clearly appears that both of the system now agree on the dynamics and therefore on the results, meaning that it is necessary for one of the system to assume the presence of a new force. Non-inertial frames of reference are systems that possess an acceleration compared to ones who don't. The laws of physics in this system differ from one another due to the fact that these accelerations are not accounted for. In order to establish the connection between these systems, we need to introduce new forces called fictitious forces. To get a full and comprehensive list of all the fictitious forces, we will now look at a more complex example. In this example, we'll have one system that is locked in the center, while the other is translated, rotated, and rotates on itself with an angular acceleration while going around the original system. In order to fully understand how to derivate these forces, we will need to start by looking at the position values. Here, we listed the first vector called the inertial frame position coordinates. Each of the three coordinates that make this vector up can depend on time in different ways. The next vector is a translational vector that determines the shift done by the non-inertial frame. RT is a 3x3 rotational matrix that is quite complex. This is due to the fact that the system rotates on itself with a certain angular speed. The reason why it is written in this complex manner will be understood shortly. Lastly, we have the vector of the non-inertial frame positional coordinates that, as we have seen, depends on time. The next step is to derivate each of the components in respect to time. This derivation is done in order to understand the velocity values in each system. While most of the values here are self-explanatory, I would like to add something on the derivative of the rotational matrix. This term can be transformed into an omega matrix multiplied by the original rotation matrix. This matrix is known as the angular velocity matrix and can be reworked as the cross product between the angular velocity vector and the rotational matrix. The last step is to further derivate this equation one more time. And now we can finally obtain the acceleration values in each system. Let's break down each component. The first part is called translational acceleration, and it refers to the acceleration the non-inertial system may have if it translates from the inertial one. The second term is called Euler's acceleration. As we can see by its terms, it is present if a non-inertial system rotates on itself with an angular acceleration. To better understand this vector, we can look at this example. Here, we have a rotating disk and a ball placed over it. Our point of view is from an inertial system, meaning that as the disk starts to accelerate, we can see that the movement of the ball is unaffected by it. We now switch our point of view to be the same as the disk. This is basically as if we were sitting on the disk as it accelerates. As a result, we will see the ball starting to accelerate in the opposite direction, and this acceleration is given by the Euler force drawn here. The third term is called centrifugal acceleration. This term is composed of two cross products in order to give this vector a very specific direction. This acceleration comes into play, for example, when we are inside a car and we take a turn. The force that pushes us to the side is the centrifugal force. The fourth term instead is called Coriolis acceleration. This term is quite a tricky one, since it involves cross products between the angular velocity and the relative speed of the non-inertial system. To better understand, we can go back to the rotating disk. As mentioned before, we have a point of view of an inertial system, and as the disk starts spinning, we can see that the ball, that moves in a straight line, is not affected by any fictitious force. If we now switch point of view to be on the rotating disk, the Coriolis force will make the ball have a complete different trajectory. The last term is the acceleration of the object that we are analyzing in the non-inertial system. If you enjoyed the video, subscribing helps me out a lot. Also, don't forget to leave a like and comment what topics you would like me to cover next. Have a wonderful day.